Okay, let's see what the momentum is. Momentum is a quantity defined in 17th century by Sir Isaac Newton, but for understanding its meaning, let's start by a simple example. Suppose that I have a train here, and this train is going to penetrate the sand hill. I move the train with a certain velocity, and then it hits the sand hill, it penetrates a little bit in the sand hill. Okay, the mass of the train is m and the velocity is supposed to be v here in this experiment. If I'm going to have more effect on the sand hill, I mean the train goes or penetrates more to the sand hill, one strategy could be increasing the mass. Suppose that I double the mass of the train, and so I know that if I move the train with the same velocity, it will have more effect, even if it has the same velocity. The greater effect is because of the greater mass. Another strategy could be moving the same train with the same mass, but with the greater velocity. If I have a greater velocity here, again I expect more penetration. So, increasing the mass of the train and increasing the velocity of the train will make greater effect when it hits another object. For this reason, physicists defined a quantity like this, momentum. This is the notation of momentum, mostly is denoted by p. It is a vector, and it's equal to mass times velocity. So if somebody asks you what the momentum is, you can define it as product of mass and velocity. Automatically, it is a vector because mass is not a vector, it's a scalar, but velocity is a vector. So if I multiply the scalar with a vector, I will get a new vector. P will have the same direction of velocity, but it is a little bit different because it's defined in dynamics. It's entangled with mass. In SI units, I expect the units of this quantity will be kilogram meters per second, because mass is in kilogram and velocity in meters per second. Newton's second law of motion could be represented again with respect to definition of momentum. Suppose that this is average acceleration, which is defined as change in velocity over change in time. You know, this bar sign indicates the average. Of course, I can have a footnote here, AV, to indicate the average. This index or this bar sign will be the same. Okay, I multiplied both sides of this this equation by mass. So left side will be ma and the right side m delta v over delta t. From the Newton's second law of motion, I know that this is the force exerted on the mass, but at the right side I have mass times delta v over delta t. Delta in physics mostly indicates change, so I expect delta v to be change in velocity. If I suppose that the mass of the object here is a constant quantity, so I can put the mass inside delta because there is no change in this quantity. So m delta v could be represented in another form like delta mv. As you see, mv here is the same quantity I mentioned before. This is momentum. So force is equal to change in momentum over change in time, rate of change of momentum. As you see here, this average or a bar sign here indicates at the left side I have average force, and at the right side delta p over delta t. So if I'm talking about average force exerted on a system, I can measure change in momentum from in a time interval. For example, suppose that it starts from t1 to t2. At t1 it could have the momentum of p1. At t2 it could have momentum of p2. So change in momentum will be p2 minus p1, which could be delta p here. Okay, let's go ahead, pay attention here. In this slide I have kinematics at the left side and dynamics at the right side. I'm going to compare some quantities here. In kinematics, you remember that we have a very important graph named VT graph, velocity versus time. It could be in any form of a function. For example, here I've got a linear function. So VT graph in my example here is a line. Slope of this line indicates acceleration, you know. Okay, multiply the vertical axis by m. The vertical axis is v here, and if it is multiplied by mass, it will give momentum here. P is equal to mv. And so the slope automatically is multiplied by m. So slope is not anymore acceleration, it will be the force. As you see, it has a very good analogy here. Okay, at the bottom here, suppose that I have an acceleration time with a linear function. Of course, this acceleration time is not related to this VT graph. It's another motion. Okay, you know that the area under the graph in AT will indicate change in velocity. Area under the graph for acceleration time will indicate change in velocity here. Okay, again multiply the vertical axis by mass. So here on the vertical axis I expect to have force, which is ma, and again a linear function, but here the area under the graph is not anymore delta v. Instead, delta v has been multiplied by mass, so it is m times delta v, and m times delta v could be represented in delta p, which is change in momentum. Okay, as you see here, some quantities here in kinematics like velocity and acceleration will have big brothers like momentum and force. Okay, I hope you have got a concept of momentum here.